Welcome back to Physics 191. I'm Gerard Blanchard. This time, we'll be talking about Chapter 7, which is momentum. Momentum, as I explained before, is a quantity which, in physics terms, is conserved, meaning that there is a fixed amount of it in the universe. It's never created or destroyed, only exchanged between objects, and that makes it useful for a certain type of situation, which we're going to call a collision. And it could be a collision, or it could be an explosion, which is actually a collision in reverse. And I'll show you how that works a little bit later on. So let's talk about momentum. In physics, momentum is defined to be the product of mass and velocity. Momentum is what you get when you multiply mass and velocity together. So in an equation, momentum, which we'll symbolize with a lowercase letter p. I don't know why, but that is the conventional symbol for momentum. P is equal to mass times velocity vector. Now, mass is a scalar, but velocity is a vector. So when you multiply a scalar times a vector, you get a vector. So in other words, P is also a vector. So we have to write our equation, P vector is equal to mass times velocity vector. So momentum, being a vector, has both magnitude and direction. The units of momentum are kilograms times meters per second. Kilograms from mass, meters per second from velocity. So, once again, momentum vector is equal to mass times velocity vector. That's our definition. That's what we're defining this new entity, or this new quantity, momentum, to be. We're making it up at this point. We're multiplying mass times velocity and calling the result momentum. Now, momentum is a vector, so it has both magnitude and direction. In other words, if you have 1 kilogram meter per second of momentum in the x direction, that's different than 1 kilogram meter per second in the y direction. Both have the same magnitude, or the amount. You have 1 kilogram meter per second of momentum, but the direction matters. So 1 kilogram meter per second of momentum in the x direction is different than 1 kilogram meter per second of momentum in the y direction. So we have to be careful to keep our directions, keep track of our directions, and keep our x and y parts of momentum separate. Okay, so we've defined this new quantity, p vector, or momentum vector, equals mass times velocity vector. Let's relate this to what we already know. Specifically, let's bring in Newton's second law, which is acceleration vector is equal to the total force vector divided by mass. I'll replace acceleration with change in velocity over change in time to get a new equation. Change in velocity vector over change in time is equal to the total force vector divided by mass. I will multiply mass, both sides by mass, and also multiply both sides by change in time to get a new equation. Mass times change in velocity is equal to total force vector times change in time. Well, let's think about mass times change in velocity. If momentum is mass times velocity, and mass doesn't change, the mass of an object doesn't change, then mass times change in velocity is the change in the object's momentum. So, we have the change in an object's momentum vector is equal to the total force vector acting on that object times the change in time, or the length of time over which that force was applied. So that's where we were working to get to here. The change in an object's momentum is equal to the total force applied to an object times the length of time over which that force is applied. And out of this and Newton's third law, we get conservation of momentum. Conservation of momentum is a direct consequence of Newton's third law, and I'm going to do this something similar to what we did for work. And I will say that if object 1 exerts a force on object 2 for a certain time, then object 2 exerts an equal and opposite force on object 1 for the same amount of time. So the change in object 2's momentum is the force that object 1 exerted on object 2 times the amount of time over which these two objects interacted, and we'll add in the change in object 1's momentum, and that's equal to the force that object 2 exerts on object 1, which is equal and opposite, or is negative force 1, 2 vector times the change in time. And when we add these up, when we add the change in object 1's momentum to the change in object 2's momentum, we get the total change in momentum on the left-hand side, and on the right-hand side we get 0 because we're subtracting something from itself. So finally, the total change in momentum when two objects interact is 0, or the total momentum that we have finally is equal to the total momentum that we have initially. So any change in one object's momentum comes from an equal and opposite change in the other object's momentum, or the total amount of momentum in the universe is constant, and it's exchanged between objects when forces are exerted, when objects exert forces on one another. So this brings us to a new type of situation, which we'll call a momentum situation. How do you identify a momentum situation? Two objects interact. Usually they collide. It could also be, as I said, an explosion. But this interaction changes their speed. So our general equation when we have a momentum situation is that the total momentum finally is equal to the total momentum initially. Now, since this is a vector equation, it's actually two equations, and the total momentum in the x direction finally is equal to the total momentum in the x direction initially, and the same for y. Total momentum in the y direction finally is equal to the total momentum in the y direction initially. Let me illustrate that with a few examples, which you can work with me. Let's have an object moving in the x direction. Let's give it a mass. Well, it's mass 1, and we'll give it a mass of 2 kilograms. And we'll say that it's moving at a speed of 5 meters per second. And we have another object, mass 2, we'll call that 3 kilograms, and V initial for it is 0, so it's initially at rest. So we have a 2 kilogram object sliding, and it collides with the 3 kilogram object, and let's say that they stick together first off. So they collide, bang, and then afterwards we have the 2 and the 3 stuck together, so we have a 5 kilogram object, and we would like to know how fast they're sliding afterwards. So this is our initial situation, and this is our final situation. Okay, so we have colliding objects. They're interacting, they're changing their speed, which means that when they collide, they're exerting forces on one another. But since we're considering momentum, we don't have to worry about those forces. We don't have to worry about the forces, and we don't have to worry about the time. We can go straight from initial to final using our equation, P total in the x direction initially is equal to P total in the x direction finally. That is our general principle here, that momentum stays the same from initial to final. So how much momentum do we have initially? We have 2 kilograms moving at 5 meters per second. That's mass times velocity, plus 3 kilograms times 0 initial velocity equals what we finally have is a 5 kilogram mass moving at V final. And so initially we have 10 kilogram meters per second of momentum. And finally we have 5 times V final. So that tells us, if I divide both sides by V, that V final is equal to 10 over 5, or 2 meters per second is equal to V final. That's how we use momentum when we have objects colliding. We draw out the initial situation and the final situation, and then we use the idea that the total initial momentum in the x direction, in this case, is equal to the total final momentum in the x direction. We work out mass times velocity. It gives us mass times velocity. And we work it out, and we can find V final. Let's do another example of this to illustrate the idea. Let's have our 2 kilogram mass moving at 5 meters per second overtake and collide with our 3 kilogram mass moving at, let's say, 2 meters per second. So this mass is moving faster than this mass, so it will overtake it and collide with it. And let's say that they stick together. So bang, they collide. And finally, we have 2 stuck to 3, and they're moving at some V final. The question is, what is V final afterwards? Start working that, please, and I'll work it slowly, but I'll let you try to stay ahead of me. Remember that our equation is P total x initial, and this is initial, and this is final. P total x initial equals P total x final. Initially, we have 2 kilograms of mass moving at 5 meters per second. And we have to add in 3 kilograms of mass moving at 2 meters per second. And that's, in the end, is equal to 5 kilograms of mass moving at V final, or 10 plus 6 equals 5 V final, or 16 divided by 5 is equal to V final. And 16 divided by 5 will be 3.2 meters per second is equal to V final. So the final mass is moving a little bit faster than it was when mass 1 was at rest, when mass 2, when the 3 kilogram mass was at rest. When the 3 kilogram mass was at rest, the whole thing was moving after the collision at 2 meters per second. Now it's moving at 3 meters per second because we had the additional momentum of the 3 kilogram mass moving at 2 meters per second. Let's take a look at another illustrative example. Now, let's consider what happens if we have our 2 kilogram mass moving at 5 meters per second, and now our 3 kilogram mass is moving towards the 5 kilogram mass at 2 meters per second. And they collide and they stick together so that we have 2 and 3. They're moving at some V final, which for the time being I'll assume is in the positive x direction. So this is our initial situation, and this is our final situation. And I'll give you a moment to work on that. Remember that momentum is a vector, so that you have both magnitude and direction, or in other words, direction matters. So try and work on this, and remember that direction matters. I'll work it slowly so that you can stay ahead of me. Our equation, as always, is momentum total initial equals momentum total final. Momentum is mass times velocity, so I have 2 times 5 from the first object. And now I have to add in the momentum from the second object, which is its mass, times its velocity. But its velocity is in the negative x direction, so that's a different situation than when it was moving in the positive x direction. So we represent that with a negative 2 meters per second, or 3 times negative 2. So 2 times 5 is the momentum of the first object, plus 3 times negative 2. Momentum is a vector. We have to take direction into account. Is equal to 5 kilograms, finally, times V final. Okay, let's see what that gives us. That gives us 10 minus 6 is equal to 5 V final, or 4 divided by 5 is equal to V final, or 0.8 meters per second is equal to V final. So if this mass is moving towards if mass 2 is moving towards mass 1, then the final object will have less momentum. It will be moving at a slower speed because overall we have less momentum. This would be positive momentum in the x direction. This would be negative momentum in the x direction. So we're subtracting off from the total momentum that the final object can have. Let's do another example like that. We'll have our same 2 kilogram mass moving at 5 meters per second. And we'll have our 3 kilogram mass moving at 4 meters per second. Towards it, they collide, and they stick together, and we're left with a 5 kilogram mass, we're left with a 2 plus a 3 kilogram mass moving at some v final, which for the moment I'll assume is in the positive x direction. That's our final situation. Work that one out, please. Okay, we have the total x momentum initially equal to p total x final. And we have 2 kilograms moving at 5 meters per second, 2 and 5, plus 3 kilograms moving at a negative 4 meters per second. 3 times negative 4 is equal to 5 times v final. So we have 10 minus 12 is equal to 5 v final, or minus 2 over 5 is v final. Or minus 0.4 is equal to v final. And really this should be vx final. So we get a negative number for our final velocity. That's okay. All it means is that we chose the wrong direction up here. The final mass is not moving in the positive x direction afterwards. It's actually moving in this direction after the collision. Or in other words, this object has more momentum in the negative direction than this object has in the positive direction. So the total momentum is in the negative direction, the negative x direction. So after the collision, when they stick together, the momentum has to be in the negative x direction. And we know that it will be moving at 4 meters per second in the negative x direction. Okay, let's do another illustrative example. Okay, let's take our 2 kilogram mass moving at 5 meters per second, and it's going to collide with our 3 kilogram mass, which we'll say is at rest. So that's our initial situation. And it collides, and after the collision, they do not stick together. So our 2 kilogram mass, let's say, is now moving at 1 meter per second, and our 3 kilogram mass is moving separately at some v final. Now, if we look at our equation, we only have one equation. P total x initial equals P total x final. So if we only have one equation, we can only have one unknown. So if the objects don't stick together, then we have to be given one of the final velocities. We can't have two separate final velocities because we couldn't solve for that in one equation. But if they don't stick together and we're given one velocity, then we can figure out what the other final velocity is. So go ahead and use this equation and figure out what v final is for the 3 kilogram mass. I'll work it out slowly so that you can stay ahead of me and get your practice. Initially, we have 2 kilograms times 5 meters per second plus 3 kilograms times 0. And finally, we have 2 kilograms times 1 meter per second plus 3 kilograms times some unknown V final, or 10 kilogram meters per second initially is equal to 2 kilogram meters per second finally, plus 3 V final, or 10 minus 2 is equal to 3 V final. So that tells us that 8 over 3 is equal to V final. And 8 over 3 is 2.67. 2.67 meters per second is equal to V final. So if they don't stick together, and this one is moving with 1 meter per second finally, then the other, the 3 kilogram mass, must be moving with a velocity of 2.67 meters per second in the positive x direction. That's x. So these are a lot of examples of using your conservation momentum. We've only done one direction, but the same would hold if we had objects moving in 2 directions. You would have to conserve separately the total x momentum and the total y momentum. Let me give you one more example, and let's say that initially we have a 2 kilogram mass and a 3 kilogram mass, and they're both initially at rest. And let's say that we have a spring or something in between them, and that's our initial situation. And the spring pushes on both of these objects so that they in effect push on each other. And finally, we have the 2 kilogram mass moving to the left at, let's say 4 meters per second. Then the 3 kilogram mass will be moving to the right with some V final. And the question is, what is V final? This is our initial situation. This is our final situation. Well, in this case, we still have conservation momentum since only the 2 objects were interacting through the spring. Let's say that the spring is attached to the 3 kilogram mass. So the spring pushed off on the 3 kilogram mass and the 2 kilogram mass, so that we have the entire system in our equations when we look at the 2 and 3 kilogram mass. In this case, we still have P total initial equals P total final, P total x initial, P total x final. Initially, we have 2 times 0 plus 3 times 0 is equal to 2 kilograms moving with a velocity of -4 meters per second plus 3 kilograms times V final. Well, this is 0 is equal to -8 plus 3 V final, or 8 divided by 3 is equal to V final. So same as we had before, actually. 2.67 meters per second is equal to V final. So this is an example of what we would call an explosion. The 2 objects are together, and they could have been propelled apart by a spring or by an explosion. That would work as well. It could be one single 5-kilogram object to begin with, and poof, it explodes into two separate parts. If we know the velocity for one of the parts, then we can calculate the velocity for the second one using conservation of momentum. As long as we have all of the interacting objects in our system, we can use conservation of momentum to answer questions about the final speed. Okay, that's a lot of examples. Let's look at the kind of question that you might be asked. A 2-kilogram object is at rest on a perfectly frictionless surface when it is hit by a 3-kilogram object moving at 8 meters per second. If the two objects are stuck together after the collision, what is the speed of the combination? This should be familiar by now, so go ahead and draw your diagram, list your knowns and unknowns, identify this as a collision, which is a momentum situation, write down your starting equation, and go ahead and solve this. I'll give you some time to get a head start. Okay, our diagram is going to be very similar to what we did in our examples. We'll draw our x-axis. We'll have mass is equal to 2 kilograms, and V initial is equal to 0. Oops, actually I'm going to have to, this is the one being hit. It is a 3-kilogram object. Mass is equal to 3 kilograms, moving at V initial is equal to 8 meters per second, collides with it. Okay, so that's our initial situation. And our final situation is that they stick together. 3 and 2 stick together, and they're moving with some velocity, V final. That's our final situation. Our starting equation, if we identify this as a collision, our starting equation is P total final, P total initial is equal to P total final, and make sure we recognize that we're working in the x direction. So P total initial x equals P total final x. What do we have initially? We have 3 kilograms times 8 meters per second plus 2 kilograms times 0 meters per second is equal to 5 kilograms times V final. 3 times 8 is 24 is equal to 5 V final, or 24 divided by 5 is equal to V final, and that would be 4.8 is equal to V final. And we're working in basic metric units, so we know that that must be 4.8 meters per second. So the answer to the question is once these two objects collide and stick together, they're moving with a speed of 4.8 meters per second. Let's try another question. In this case, we have a rifle that has a mass of 4.5 kilograms, and it fires a bullet of mass 10 grams at a muzzle speed of 820 meters per second. And the question is, what is the recoil speed of the rifle as the bullet leaves the gun barrel. Think about momentum, draw your diagram, list all your knowns and unknowns, and try and answer that question. Okay, I will draw the rifle and the bullet as both blocks. They're both V. They both have a V initial of 0. The mass of the rifle is 4.5 kilograms. The mass of the bullet is 10 grams, which we will have to convert. 1 kilogram is 1,000 grams. So the mass of the bullet is 0.01 kilograms. And I did that conversion that way because you do have to be careful. If you're off by even 1 decimal place to the left or right, your answer won't be right. So you have to be very careful about those conversions. That's our initial situation. Initial. And our final situation is that we have the bullet moving with a speed of 820 meters per second, and presumably we have the rifle recoiling in the negative x direction with some V final. And the question is, what is V final? Well, this is an explosion. The only objects that we have that are acting on each other are the rifle and the bullet. So we can still use our momentum equation. P total x initial equals P total x final. Initially, we have 0 because nothing's moving. Finally, we have the bullet, which is 0.01 kilograms, moving with a velocity of 820 meters per second. Plus the rifle with a mass of 4.5 kilograms that's moving with V final in the negative x direction. So I'm going to put the negative in already, negative V final. So I'm assuming that it's moving in the negative x direction. And that gives us 0 is equal to 8.2 plus 4.5, or minus 4.5 V final. I'm going to add 4.5 V final to both sides. 4.5 V final is 8.2. That gives us V final is 8.2 divided by 4.5, or V final is equal to 1.82 meters per second. And so since we got a positive number, we know that we did pick correctly in the direction that the rifle would be moving finally. In other words, it's moving in the direction opposite the bullet. And we know that it's moving at a speed of 1.82 meters per second. So that is why when you fire a rifle, the rifle kicks back or moves back in the direction opposite the bullet, because the system that's interacting is the rifle is exerting a force on the bullet, and the bullet is exerting an equal and opposite force on the rifle, which makes us conserve momentum. So the bullet, which is very small with a very high speed, moves in one direction, and the rifle, which is very large, moves with a smaller speed in the opposite direction. Those are a couple of examples of using momentum to answer questions. We'll have more exercises next time, but let's just remember what we talked about this time. We introduced the concept of momentum. Momentum is defined to be an object's mass times its velocity. And because of Newton's third law, whenever two objects interact, the total change in momentum is zero, because momentum is exchanged by forces. So whatever force one object applies to another, the second object exerts an equal and opposite force on the first. So whenever two objects interact, the momentum of the individual objects may change, but the total momentum never does. If we consider a system that comprises all of the interacting objects, then whatever total momentum we have before, we will have the same total amount of momentum afterwards. So even though the forces could be very hard to figure out when two objects collide, we can still calculate the consequences of a collision by going straight from before the collision to after, using conservation of momentum. A little bit later on, I'll show you how you can estimate the forces involved in a collision using momentum ideas. But for right now, we're just interested in the consequences of the collision, which we can calculate using the idea of conservation of momentum. So until next time, think momentum and think physics.